This is my presentation for Lab 5 on the human. Our objective is to model Felix Baumgartner's position and velocity over time during his free fall from almost 37,000 meters. We will need to find an accurate model of air resistance for that height because density and temperature of the air will be variable, and we will use Newton's second law to update velocity and position over time, and the drag equation to update net force. We are interested in the answer because it will show us how to model drag force with variable air temperature and density and how much of an impact each of those variables have on the result. First, I will go through the initial information I've been given, then I will discuss how I model drag, temperature change, and air density change, and finally I will go over the final results and a few discussion questions. So for my background information, we know his initial height is about 37,000 meters. His final height is about 2,600 meters because he does not land at sea level. We know his maximum velocity was 428.75 meters per second, and the length of his entire fall was 260 seconds, and that his mass is 118 kilograms, and that the only forces we need to take into account are gravity in the negative y direction and drag in the positive y direction. And so here's how I input all of that into GlowScript. I use the code from Lab 2 on the motion of a falling object as a template to add my own information into. So the simpler model to find terminal velocity would calculate drag as proportional to velocity, which would show his velocity increasing quickly at first, then his acceleration decreases. His velocity would not decrease though until he reaches terminal velocity. But his velocity actually increases quickly and then begins to decrease in magnitude, which defies that model. And this is likely because of the change in air density and temperature as he falls through the atmosphere. Because of this, we must use a more complex model. And here's how I did that. Rho is air density, V is velocity, C sub d is the drag coefficient, and A is the cross-sectional area. We don't know the drag coefficient or the area, so we'll need to calculate them. So to do this, I set the drag force equal to the force of gravity, as would occur when he reaches terminal velocity, and then I will use the maximum velocity he reached as that velocity. And then the air density I used was from a density calculator I found online that estimated to be about this. And so now that we have the drag coefficient and the cross-sectional area, I need to update air density for each height. And we know that Felix's initial temperature was 248 degrees and his final was 271 degrees Kelvin, and that his total time was 260 seconds. So I can calculate the average of his change in temperature, and I'm aware that his temperature doesn't actually change linearly like that, but this is the only way I know to model it, and it is a reasonably accurate approximation. And here's how I input all of that into GlowScript. And here are my results. You can see that he starts up here, and he falls very quickly until he reaches about the 75-second mark, where he starts to fall slower until he reaches a little bit above sea level because he does not land at sea level. And here's my chart for the velocity in the y direction versus time. You can see his velocity increases quickly until about the 40-second mark, and then it decreases quickly, and it continues to decrease until he lands. This is because of differences in temperature and air density. And so here's my results. The final height I calculated was 2,233 meters, while the actual was 2,567 meters, which is a 15% error. And the maximum velocity I calculated was 303.8 meters per second, while the actual was 377 meters per second, which is a 19% error, and these differences are due to imprecise temperature and pressure. And this is my first discussion question. What effect does a change in density of air with altitude have on your predictions? So based on the drag formula I used in my model, which I have over here, we know that air density is directly proportional to the force of drag, so as Felix gets closer to sea level, air density increases and so does drag. This means that I would predict Felix's velocity increases quickly at first, because this is when air density is the lowest, and then decreases as he descends. And this matches my experimental data. And here's my second discussion question. What effect does a change in temperature with altitude have on your predictions? So based on the formula I used to update air density, we know that air density is inversely proportional to temperature, and it is directly proportional to drag. And so we know that temperature is inversely proportional to drag, so as temperature increases, drag will decrease, and vice versa. And because we know the temperature is inversely proportional to drag, we would expect the drag force to increase while he was falling through the stratosphere because temperature is decreasing, and then drag should decrease while he falls through the troposphere over here on my chart, because you can see the temperature is increasing. But because I used a linear approximation of temperature change, this is now reflected in my data. And so, in conclusion, in this lab we modeled Felix Baumgartner's free fall using the drag equation and Newton's second law, along with a basic understanding of how air density and temperature changes throughout Earth's atmosphere. And this model was able to accurately approximate his path, but in the future I would like to find a more accurate model for temperature to hopefully reduce some of the error in the final answer.